All right, next up, we have energy changes associated with a change in state of matter. These are also known as phase changes. So the energy absorbed or released, so absorbed if it's an endothermic process, release if it's exothermic, during a phase change is in the form of potential energy. And during a phase change, we've talked about this before, temperature is constant. So for example, when water is boiling, during that time which the water is boiling, its temperature does not change. Any energy that is being added is in the form of potential energy, which is being used to change the liquid into a gas. And so this is important because that means if the temperature is constant during a phase change, then so is the kinetic energy. So there is no change in kinetic energy. So that means that we cannot use Q equals MCAT to do any sort of calculation involving the energy associated with a phase change. So instead of using Q equals MCAT and the specific heat of a substance, we're going to use some different constants. One of them is called the heat of fusion. So the symbol, sorry, I don't have room, I would put it to the left. So a symbol for heat of fusion is delta H FUS. Don't worry about what delta H means just yet. Uh, just change in heat content technically. Delta H FUS, heat of fusion, is a constant for a substance. And so it says the heat of fusion is the energy absorbed or released, again, absorbed if it's an endothermic process, release if it's exothermic, during the solid liquid phase change. So from solid to liquid, what is that called? Okay, so we use the heat of fusion if a substance is melting. How about changing from a liquid to a solid? What is that called? Okay, so that means we can also use the heat of fusion to calculate energy associated with freezing. So we're talking about melting and freezing. So energy absorbed or released during the solid liquid phase change of 1 mole of a substance or 1 gram. So sometimes the constant is given to you in kilojoules per mole, and sometimes it's given to you in joules per gram. So make a note of that. Usually heat of fusion is given in kilojoules per mole of the substance undergoing the change. The constants in our book, I believe, are all in kilojoules per mole, but sometimes it could be in joules per gram. So let me restate that again. Anytime a substance is either melting or freezing, we can use the heat of fusion to calculate the amount of energy involved in that process. So melting is endothermic, freezing is exothermic. Either way, heat of fusion. Next up, we have heat of vaporization. Like heat of fusion, heat of vaporization is a constant for a particular substance. This is the energy absorbed or released during the liquid gas phase change of 1 mole of a substance or 1 gram of a substance. So let's talk about liquid gas phase changes. What is it called when a liquid turns into a gas? Now, collectively, we can say vaporization, but vaporization here, what we're looking at primarily is not evaporation, but boiling. So if we're trying to calculate the amount of energy required to boil a liquid, we can use the heat of vaporization. How about gas to liquid? What is that called? That is known as condensation. So if we wanted to calculate the amount of energy released when a gas condenses, we can use the heat of vaporization. So symbol we use for heat of vaporization, delta H VAP. And again, that's usually in kilojoules per mole. Could be in joules per gram. So there's a table, actually a really big table in the back of your book, pages 855 to 857 for all of the elements. And just looking in here, looks like heats of vaporization and heats of fusion are in kilojoules per mole. Uses a different term in that table, uses enthalpy of vaporization. Enthalpy? I don't like that word enthalpy, so I use heat. Enthalpy of vaporization, enthalpy of fusion. Make sure you know which constant to use for which example you are working on. Just like you need to memorize the values for, or the value rather, for specific heats of water, you also need to memorize the heat of fusion and heat of vaporization for water. So heat of fusion of water, 6.01 kilojoules per mole. Sometimes I use 6.02, so I don't know which one is better. So we'll go with 6.01 here. But just know I may use 6.02 in our calculations. Or 0.334 kilojoules per gram, which is 334 joules per gram. So either one of those is fine. Heat of vaporization. What do you notice there? See a difference? Why is there a difference in the values for heat of fusion versus heat of vaporization? We'll talk about why that is the case later. So heat of vaporization of water, 40.7 kilojoules per mole, or 2.26 kilojoules per gram, or 2,260 joules per gram. All right, so how are we going to use these constants in our calculations? So let's say we're given grams of a substance that is undergoing a phase change, and we want to calculate the amount of energy needed if it's an endothermic process for that reaction to occur. So of course, anytime we're converting between grams and moles, we're going to use molar mass. How about the relationship between moles and kilojoules? Either way you go, we're going to use delta H. We've used this before. We've used delta H as a conversion factor when we're doing energy associated with chemical reactions. Same idea here, we're just doing calculations involving energy associated with physical changes in state of matter. So let's say we're given the amount of a substance in moles. Of course, our conversion factor then is going to look like this, so many kilojoules over so many moles. Let's say we are starting off with energy, so we're told how much energy something absorbs or releases. This time, moles is on top and kilojoules on the bottom. And more often than not, it's going to be per 1 mole of that substance. The only time it's not 1 mole is like what we saw with chemical reactions, where your coefficient's not a number 1, let's say, and then we're not going to have 1 mole in our conversion factor. But here, it's going to be 1 mole. So let's take a look at some examples. All right, number 1, how much energy would be required to, keyword, very, very, very key word here, to melt? How much energy would be required? So melting is endothermic. 30.0 grams of acetone. So acetone has a chemical formula of C3H6O at 177.8 Kelvin. Now, what is the significance of 177.8 Kelvin? This is the melting point for acetone. So what we're saying is the acetone's already at the melting point, and so any energy that you add to this acetone will be used just to melt it. There is no temperature change that occurs. Now, this problem is giving you a hint. It's telling you that you need to use the heat of fusion. On the test, it's not going to say whether to use the heat of fusion or the heat of vaporization. So that's why I said the key word here is melt. Anytime we see the word melt or freeze, you must think heat of fusion. All right, so let's set it up. We're going to start off, I'm going to start way over here to the left, 30 grams of acetone. And remember, look at these units here. We have kilojoules per mole. And so if we're not given the amounts of the substance in moles, we need to convert it. So let's do that. Go ahead and pause the video, calculate the molar mass of acetone. Should get 58.1. Make sure to put your units in there. Make sure to cancel your units as you go. So we have moles. We need moles to cancel. So 1 mole of acetone goes on the bottom. So for every 1 mole of acetone, how much energy is required to melt it? That would be 5.72 kilojoules. And we should be good. Go ahead and pause the video and see what you get. So if you have 30 grams of acetone that's already at its melting point or freezing points, it's going to take 2.95 kilojoules of energy to completely melt that solid and turn it into a liquid. All right, let's take a look at another example. Number 2, how many grams of water could be boiled to steam by the addition of 2,500 joules of energy to some water at 100 degrees Celsius? So again, what is the significance of the temperature? What do we do with it? We don't do anything with the temperature here, just like in the last problem. So what it's telling us is that the water is already at its boiling point, and so the energy that is being added is not going to heat it up, but rather is just going to turn that liquid into a gas. Hot water vapor we call steam. And so this time we're starting. Be careful with joules. Make sure you use the appropriate constants. Key word here, boiled. The water is boiling. I'm going to let you set this up on your own. Go ahead and pause the video and set it up. So here's the setup. I want to show you something a little different. So starting off with 2,500 joules, I want to convert that to kilojoules. So I don't always have to see this work, but it's nice to have this written out. So we have 1 kilojoule is 1,000 joules, so that joules cancels. And then I chose to use the molar heat of vaporization, 40.7 kilojoules per mole. If you use the heat of vaporization in joules or kilojoules per gram, that's fine. But I wanted to use this one. Kilojoules cancels, moles cancel, and we're left with grams. So we see it's not a lot. So 2,500 joules of energy seems like a lot of energy, but it's only going to boil 1.1 grams of water, which is just over a milliliter. That's pretty amazing. So water, not only does it have a very high specific heat, but we see here it also has a very high heat of vaporization. All right, next one. How many molecules, we're looking for this time, of ammonia would be frozen? Keyword frozen. By the removal, so freezing is exothermic, you got to take energy out in order to turn a liquid into a solid. That's what your freezer does. In fact, it takes energy out of water or foods. Removal of 1,327 joules of energy at a temperature of 195.3 Kelvin. Guess what? What is 195.3 Kelvin? That happens to be the freezing point for ammonia. So again, this is telling us that there's no temperature change that's occurring. That's just a phase change. The ammonia is freezing. All right, go ahead and pause the video and set this one up. All right, here's a setup. I ran out of room over there, so I'm gonna write it here. The answer is 1.41 times 10 to the 23rd molecules of ammonia. So just looking for molecules this time, so just want to show you something a little different using Avogadro's number. All right, let's try another, number 4. How much energy would be released? Let's find that answer in kilojoules. If 0.724 moles of water vapor, what's the key word? Condensed. So again, make sure you use the right constants. Go ahead and pause the video and set this one up. So I think the purpose of this one was to force you to use the heats of either fusion or heat of vaporization, molar heat of fusion or molar heat of vaporization. So again, keyword is condensed. So that means heat of vaporization, 40.7 kilojoules per mole. And we end up with 29.5 kilojoules of energy is required. Now, how much is 0.724 moles of water? Well, a half a mole of water is 9 grams. This is about 3/4 of a mole of water, so it's about 12 grams or so of water. Takes nearly 30 kilojoules of energy just for that much water to condense. Pretty amazing. So I know I've had you ask this question before. Why does it take water forever to heat up? Well, it takes water forever to heat up because it has such a high specific heat. How about this one? Have you ever asked, why does it take water forever to boil? You put some water on the stove, and it just takes forever for it to boil. Not just to get to the boiling point, but once it's boiling, it would take a long time for that water to completely boil away. And so the reason is water has an extremely high heat of vaporization. All right, so in reality, substances aren't always just undergoing a temperature change or just undergoing a phase change. A lot of times you have a substance undergoing both a change in temperature and a change in state of matter. So we're going to do some calculations involving combined temperature and phase changes, where you're going to use both Q equals MCATs and heat of fusion or heat of vaporization in your calculation. First, so let's do this. Let's draw a graph of temperature on the y-axis versus time. This first one is known as a heating curve. So what a heating curve shows is what happens to the temperature of a substance as you add energy at a constant rate. So let's say, let me fill in some things here. Let's say this is the melting point of a substance and this is the boiling point of a substance. So let's say we're starting down here at a temperature below the melting point of a substance. So this is water, for example. Let's say we're starting at negative 10 degrees Celsius. If you add energy, let's back up. What state of matter is a substance at any temperature below its melting point? That substance will be a solid. So if you add energy to a solid that's at a temperature below its melting point, what is going to happen to that solid? Now, a lot of times students will say that substance will melt. No, it will not. That substance is first going to heat up to its melting point. Once that substance has reached its melting point, if you continue to add energy, what is going to happen to that substance? It is going to melt. Well, what happens to the temperature of a substance as it melts? Now, some of you might be thinking the temperature goes up. No, it does not. Remember, the temperature is constant during a phase change. So while that substance is melting, its temperature remains right at the melting or freezing point. So at this point here, right here where we ended this line, the substance has completely melted, so we have all liquid at the melting point. If you add energy to a liquid that's at its melting point, what's going to happen to that liquid? Well, that liquid is going to heat up. Not forever, but it's going to heat up to its boiling point. So here we have all liquid at its boiling point. If you add energy to a liquid at its boiling point, what happens to that liquid? Don't say the temperature stays constant. I want to know what happens to the liquid. The liquid will boil. While the liquid is boiling, what happens to its temperature? That's right, it stays constant. Notice anything here about the time it takes to melt the solid versus the time it takes to boil the liquid? Why does it take more time to boil the liquid than it does to melt the solid? Well, we already talked about this. It takes more energy to boil a liquid than it does to melt a solid. So if you're adding energy at a constant rate, then that means it's going to take more time. So why is this? Let's take water, for example. Let's look at ice. When you melt ice, what's happening to the particles? Remember, the particles of a solid are held tightly together in fixed positions, whereas the particles of a liquid are able to move past one another. So when you melt a solid, what you're doing is you're breaking some of the attractive forces between the particles. What happens when a liquid boils? So remember, particles of a liquid are stuck together, they're sliding past one another, whereas the particles of a gas are not stuck together, and they're able to move around all over the place, not held together. So how does this happen? When a liquid boils, you are breaking not some of the attractive forces, but all of the attractive forces. So what takes more energy? Breaking some of the attractive forces or breaking all of the attractive forces? Of course, it takes more energy to break all of the attractive forces. That's why it takes more energy to boil a liquid than it does to melt a solid. So continuing on with our graph, so at this point we have all gas at the boiling point. If you add energy to a gas at its boiling point, what happens to that gas? It heats up. Have you ever heard that burns from steam are worse than burns from liquid water? Well, what is the hottest that liquid water can get at 1 atmosphere of pressure? That would be 100 degrees Celsius. According to this graph, what is true about steam? Well, steam can be hotter than 100 degrees Celsius. Thus, burns from steam are worse than burns from liquid water. Now, something that you need to understand is what state of matter the substance is at each part of the graph. So between here and here, the substance is just a solid. Between here and here, where the substance is melting, it's both a solid and a liquid. From here to here, so above the melting point but below the boiling point, the substance is just a liquid. During this time, the liquid is boiling, so it's both a liquid and a gas. And then at any temperature above the boiling point, the substance is just a gas. Something else that's important is you need to know whether the substance is undergoing a change in kinetic energy or a change in potential energy. So where the temperature is changing, so this part here, and this part here, involves changes in kinetic energy. And we could use the specific heat to calculate how much energy the substance has gained. Here, where the temperature is not changing, where it's melting, and here, where the substance is boiling, those involve a change in potential energy. So we can use heat of fusion if the substance is melting. We could use heat of vaporization if the substance is boiling. So this graph can help you stay organized with what we're going to do next. All right, so we also have cooling curves. Everything on the last graph was an endothermic process. So heating is endothermic, melting is endothermic, boiling is endothermic. On a cooling curve, what we're showing are exothermic processes. So again, same axes. And again, I'm going to label boiling points and freezing points. Remember, freezing points and melting points occur at the same temperature. So this time, let's start here. Let's say we have a substance above its boiling point. First of all, what state of matter is that substance? It would be a gas. So what we're trying to show here is what happens to the temperature of a substance if you remove energy at a constant rate. So if you remove energy from a gas above its boiling point, that gas is going to cool down to its boiling point. If you remove energy from this gas at its boiling point, that gas is going to condense. And while it's condensing, its temperature remains constant. Once all the gas is condensed into a liquid, if you continue to remove energy, that liquid will cool down to its freezing points. If you remove energy from a liquid at its freezing points, that liquid will freeze. While it's freezing, its temperature remains constant. And once all that liquid is frozen to solid, if you remove energy, the temperature decreases. Have you ever seen ice, for example, at a temperature below 0 degrees Celsius? I'm sure you have. Your freezer's inside temperature is less than 0 degrees Celsius. The ice in there is colder than 0 degrees Celsius, so maybe -4 or something like that. So kind of opposite profile. Again, same thing. Make sure you know what state of matter the substance is in different parts of the graph. Make sure you understand if the substance is undergoing a change in kinetic energy versus a change in potential energy. All right, so let's take a look at some more examples. Number one, calculate the amount of energy required to melt, keyword there, 1.44 grams of ice at 0 degrees Celsius, and then change it to liquid water at 47 degrees Celsius. So let's go back to our heating curve and see where we're starting and then see where we're stopping. So we have ice at 0 degrees Celsius. So we're starting right here. And then we're ending up with liquid water at 47 degrees Celsius. So this is 0, this is 100. So somewhere there. So make sure you do the calculations in the order of what is happening to the substance. So what happens to the substance first? Well, first, the substance will melt. How do you calculate the energy required to melt a solid? That's right, use heat of fusion. And then after all that solid has melted, it heats up from, in the case of water, 0 to 47. How do you calculate the amount of energy required to heat a substance? We use Q equals MCAT. So what you're going to do is nothing new. You're going to first calculate the amount of energy required to melt the solid, get that number. Then you're going to calculate the amount of energy required to heat the liquid, get that number. And then we want the total amount of energy involved in this process. So you're going to take those two values, make sure they have the same units, and then add them up. So once you try this, since this is nothing new, I think you can do this on your own. Pause the video, set it up. So first step, use the heat of fusion to find out how much energy it takes to melt the ice. We get 0.481 kilojoules, I believe. Next, to heat the water from 0 to 47. So I just made that temperature change positive. Technically, it is TF minus TI anyways. But if it was cooling down, still just use the absolute value of the change in temperature is fine. We get 283 joules. So what is the total amount of energy? So we got to add these up first, though. Either convert the kilojoules to joules or the joules to kilojoules. I chose to convert this kilojoules to joules. And then I added them up. And so the process as a whole requires 764 joules of energy. All right, let's try another one. Number 2. Calculate the amount of energy released. So we got exothermic process. Condensing is exothermic. So change the wording. I think it says required to. Condensing is exothermic, so put release. Released to condense 98.7 grams of steam at 100 degrees Celsius, and then convert it to liquid water at 47.0 degrees Celsius. All right, go ahead and pause the video and see what you get. So similar approach, first step is to find out how much energy is released when the steam condenses. So we're going to use the heat of vaporization. So 223 kilojoules of energy is released just when the steam condenses. And then that liquid water is going to cool down. The delta T is not 47 this time. It's cooling from 100 to 47. The difference this time is 53 degrees Celsius. If you did 2 sig figs, that's fine. That would be, I guess, 22 kilojoules. Notice I converted it already to kilojoules. Add those up and you get about 245, 240, yeah, 245 would be fine. 245 kilojoules of energy. All right, one more. Go ahead and work this one out. Everything that you need is given to you. The chemical formula for methanol is CH3OH. Go ahead and pause the video and see what you get. Should end up with 47 kilojoules. Now this one's a little different. We're given the temperatures in Kelvin. Did you convert those temperatures from Kelvin to Celsius? Well, if you did, what is the difference between 337.2 Kelvin and 200 Kelvin if you converted those to Celsius? I'm going to guess the difference was 137.2 degrees Celsius. What's the difference between 337.2 Kelvin and 200 Kelvin? That's right, 137.2 Kelvin. So technically, when we have specific heats, the units are joules per gram degrees Celsius, or because the difference between corresponding Celsius and Kelvin temperatures are the same, joules per gram Kelvin. So you did not have to convert those to Celsius. You could have left them in Kelvin. All right, that concludes this lesson. If you have any questions, please let me know. Thanks for watching.